At t equal to 0, when the switch is closed, inductor blocks the current completely. Current is 0. This is I versus t graph. Inductor obviously builds an EMF which cancels this EMF at t equal to 0. But then current builds, increases and increases, and finally it attains some maximum value, which is just E by R. It's just like that inductor becomes a straight wire at steady state, right? So that steady state value, which I have called as I infinite, is E by R. Practically infinite time is not so much. So that's the case of growth of current. So what is to remember here, that at t equal to 0, inductor behaves as an open circuit. Open circuit. It's like a cut in the circuit. And at t infinite, inductor behaves as short circuit, just like a normal wire, having no magnetic effect. Now, when I say no magnetic effect, I am referring to induction. I am not saying that there won't be any magnetic field inside inductor. It will be very much there. If current is flowing, which is E by R, through that inductor, if it is solenoid, for example, then there will be magnetic field inside it. But steady magnetic field doesn't give rise to any induction effect. So induction is not there at steady state, right? Now this thing, T divided by L by R, is called the time constant. Tau is L by R, which is called the time constant. And it is time, of course. And what is the significance of time constant? If you put T equal to tau, if you put T equal to tau, it will be e to the power minus 1. And 1 upon 2.7 is around 0.37. 1 minus 0.37 is 0.63. Approximately 0.63. So in time constant, in one time constant, current reaches 63% of its maximum value, 63% of E by R. In one time constant, current reaches 63% of its full blast value. That's the meaning of time constant. So at one time constant, 63% will be somewhere here. That's what the point will be at one time constant. It is a saturating type of growing function. When I say saturating type of growing function, it means that growth rate is slowing down. Growth rate is slowing down. Population growth is a rapid growing function like this. Exponential function is a rapidly growing function. Always remember two similarities and dissimilarities of exponential and logarithmic functions. Both are increasing, that's a similarity. Log is also increasing and e to the power is also increasing. But log grows in a sluggish manner, whereas e to the power grows in an aggressive manner. So this is a sluggish type of growth. Just like log function has sluggish type of growth. Eventually this particular function attains peak value. But e to the power function, well, it will go to infinite only, eventually. When we talk about decay, you already have some steady state current. You already have some steady state current. And then you are quickly removing the battery from the system. Maybe there was some wire connected via connected via switch, and you activate that switch so that the battery is shorted. Some mechanism you can employ. Well, short circuiting battery may not be a good idea, practically speaking. So I must say some different mechanism is employed. So you quickly remove the battery at t equal to 0. The steady state current was already established. So let's say the battery was here, and this current was steady state current, and that was E by R, right? Okay. Now, we remove the battery somehow. There are two approaches. One is the common sense approach to decide the sign plus minus. Other one is the mathematical approach. If you follow common sense approach, then the inductor will try to maintain current. It would not like current to fall. So common sense approach will say that this has to be the positive terminal so that the current can be sustained in the external circuit. Current can be sustained in the external circuit, right? Inside the battery, current flows from minus to plus, but it is the external circuit that matters, in which it flows from the plus of the battery to the minus of the battery, plus to minus. So in the external circuit, through this resistor R, this inductor would not like current to fall. That's one way of thinking. We can always talk in terms of the self current also. Current through it should be maintained as well. That's self-inductance, so obviously that we can say self-inductance. So this approach will give you positive here, but you can also go for mathematical approach. You can say that this was the positive terminal of the battery. So the battery which is here, the electromagnetic battery if you like, which is here, it has plus here and minus here, and if it is plus, if it is minus, then the EIND is given by minus L di by dt. That's the mathematical approach. Minus L di by dt with this type of sign scheme. Both approaches are fine. Now, whichever way you want to do. If you want to do it the mathematical way, then you will say that if you walk from here, minus terminal comes, so minus EIND, then plus comes, so plus IR equal to 0. But then you will say that EIND is minus L di by dt, mathematical approach. So L di by dt plus IR equal to 0. If you use that other approach, in which you can say with surety that yes, it has to be plus. In mathematical approach, you don't say with surety that this has to be plus. You let the mathematics decide if it is plus or minus. You just put plus there, right? But in the other approach, you are saying with certainty that yes, it has to be plus because in the current has to be maintained. So minus minus will be plus, then IR equal to 0. This is going to be a simple differential equation, very simple in fact, di by I, then constant. In fact, R by L you can keep on whichever side, R by L or L by R, whatever, doesn't matter. When time is 0, let's say current was I0, steady state current, and when time is t, let the instantaneous current be I. So on integration, you will get log of I by I naught equal to minus RT by L, and that will eventually get you I equal to I naught e to the power minus RT by L, which can be written as this, where L by R is the time constant tau. So I naught is the initial value, and it is multiplied to e to the power negative x type of function, which is a falling function. So obviously current will fall and fall and fall and fall. But it won't happen immediately. Normally what you expect, you have got battery, you have got resistor, you switch off, gone, current becomes zero immediately, that's what you expect. It doesn't work like that. There is some lag involved. And greater the inductors, greater would be the lag, right? And that can be seen here. I equal to I naught e to the power minus t by tau. It's a falling function, just like e to the power minus x function. And if time is infinity, it will become zero. Infinity practically is not as big as it sounds by the word infinity. Practically it's not as big as that, as it sounds. But there is delay involved. Now while we talk about inductors as some coil sort of thing, practically if you speak, even ordinary wires have got some inductive effect and even some capacitive effect. But we don't have to get into that. That's discussed in electronics, etc. But that example I'm giving you to tell you that there is some delay in any case, whether little or more. You know e to the power minus x function very well, but nevertheless, yes, e to the power minus x function can go here also if we discuss in mathematics, but in physics context, you won't make t less than 0. So don't bother about this part. Just start from here, t equal to 0, and then keep on going and going. The discussion of LRC circuit, LR circuit, is also used to talk about energy. And then we say that it's a general result. Let's say we have this L, this R, and this E. At an instant, current is I. Just apply the Kirchhoff's loop law. You can possibly walk from here. You face negative, put a minus. And if you go for mathematical approach, then if current is coming like this, then this is plus and this is minus, and it is minus L di by dt, EIND. So we face minus, put minus. We face minus, we put minus. We face plus, we put plus IR. And then EIND is minus L di by dt. And then we multiply by I. Intentionally we do that. And we get EI equal to I square R, then Li di by dt. Right? and then we integrate with respect to t. ei dt, I square r dt, il di. We integrate when time is 0, current is 0, let's say. So let me also say that I'm talking about a growth circuit. At t equal to 0, nothing was there, and suddenly the switch was closed at t equal to 0. So when t is 0, current is 0. When t is t, current is I. Now look at this, and look at this. 0 to t integral I square r dt. You know what is I square r? And you know its power consumed by the resistor. And I square r dt will be the energy. When we say from 0 to t, it's the total energy consumed by the resistor from 0 time to t time. You know what is EI? This is the power delivered by battery. Instantaneous power delivered by battery is EI. EI dt and its integral in 0 to t time means in total time t, this is the energy delivered by the battery. This is the energy delivered by the battery. This is the energy eaten by the resistor. Well, whatever battery is giving is going to only two fellows, this resistor and this fellow, nobody else. We are assuming ideal wires. So whatever this battery is supplying is going to only two places, this and that. This is already here. So what else could this be? This has to be the energy stored by this fellow. Clearly it is storing energy. And this is 0 to IL, integral di, integral IL di. So when you integrate it, you get it as half Li square. You can check, it's very simple integral. L into I square by 2, 0 to I will be half Li square. Half Li square is the energy stored inside the inductor when the current through it is I. Now, as I said that while we get this result for this particular case, we actually generalize this result. We will say that any inductor, if you have and current through it is I, then it has this much energy, half Li square. And to generalize it even more, we say that, well, why should or how should an inductor store energy? So we say that, well, as the current is there inside the inductor, there is magnetic field, and that magnetic field is storing the energy. So we are basically saying that the magnetic field has got energy. Magnetic field has got energy is what we are saying. Earlier in electrostatics, we have said that electric field has an energy. And now we are saying that magnetic field also has got energy, and which is half Li square. But if I want to associate energy with magnetic field, then I would like B to come there. Just like in case of electric field, we got E into the picture. It was energy density, right, for electric field. We would like magnetic field to be there, not L. So, let's talk about solenoid. Again, we are going to say that while it is for solenoid, it's a general result, right? That's what we are going to say eventually. Like in case of electric field energy, what did we do? We took some parallel plate capacitor. And then we said, okay, it's a general result also. So there we took parallel plate capacitor. Here we are taking solenoid. L for solenoid has been obtained. It is given by this. So just imagine a solenoid here, and it will have this much energy. In place of L, put this I square, just copy, and divide that by the volume contained inside. How much volume is contained inside? If its radius is r, area is pi r square, length we will have to take some length. Let's say small l is the length. That is the volume. In electric field also we found the energy density, energy per unit volume. Energy per unit volume. Here also we will find energy per unit volume. So divide this by the volume, which is pi radius square times the length, and this will cancel. In fact, the whole thing will cancel. Pi r square L. It will be half mu naught n square, half mu naught n square I square. I'm intentionally multiplying by mu naught, making it square, and dividing by mu naught, because mu naught n I is b. So this becomes b square. Mu naught is in the bottom. So half b square by mu naught is the magnetic energy density. It's a magnetic energy density. Half b square by mu naught. I hope you remember what is the electric field density. Half epsilon naught E square. Half epsilon naught E square. That's the electric field density. Half b square by mu naught is the magnetic field density, energy. Epsilon naught and mu naught always have this reciprocal relationship. Now that means wherever you have magnetic field, you have energy. Wherever you have magnetic field, you have energy. Now if I want total energy stored in some region, if I want total energy stored in some region, I will have to integrate. U is given by volume multiplied by b square by 2 mu naught. If it's a constant magnetic field, the job is very easy. The integration is hardly a problem. But if magnetic field is distance dependent type, then integration is the way to go. If you want U in some region, for example, you have got a long wire. From that wire, between 2 centimeter distance to 3 centimeter distance, if some region is considered maybe like a cylindrical shell type of region, I mean hollow cylinder type of region, 2 centimeter is the inner radius, 3 centimeter is the outer radius. Energy is stored in that 2 to 3 centimeter region. Then integration. Integration is the way to go. You will take little volume dV, and then you will say in that little volume dV, the energy du, little du, is b square by 2 mu naught into dV. dV is a little volume. You will put B, formula for B, then you will integrate between 2 to 3. I think we did some problems in electric field discussion, energy associated, energy stored. It is just like that only. And note that we are talking about DC. So when we discuss LR circuit now at this stage, it is for DC. And when I say at t equal to 0, an inductor is an open circuit, it is for DC. Likewise, at steady state, it's just like a straight wire. It is true for DC. AC is coming, and in AC you will see variations. In case of AC, it won't be like that. Nothing like open circuit, closed circuit type of thing. In AC, same LR circuit. In RC circuit also you will find the difference. DC versus AC. An illustration. A solenoid has an inductance of 10 Henry and a resistance of 2 ohm. It is connected to a 10-volt battery. How long will it take for the magnetic energy to reach 1/4 of its maximum value? Well, if you connect a solenoid to a 10-volt battery, then initially it will not allow any current. Gradually current will build up. This is a case of growth. This is a case of growth. So as current builds up, energy depends on I square, half Li square. 1/4 of its maximum value. Now maximum value is half Li infinite square or half Li naught square. That's the maximum value. Either use infinite here or 0 here. So 1/4 of that, that's what energy should be. Let the current be I at that instant when the energy is 1/4 of its maximum value. Let the current be I. So the energy would be half Li square. It is 1/4 of half Li infinite square. That means I is I infinite divided by 2. You can check that. Current has reached the 50% of its maximum value. Alright. Now it should be very simple. We know that for growth, I equal to I infinite 1 minus e to the power minus t by tau. In place of I, put I naught by 2, and other numbers are given to you. L is given to you, R is given to you. Maximum current I naught will be 10 divided by 2. 10 by 2 is 5. But in fact, I naught is getting cancelled. So I wonder if this information is required at all or not. Maybe it's not required. So you put the numbers and you do the calculations. See if you are getting around 3.5 seconds. And let me know if you have any questions.
Yes, sir. Yes, sir, getting it.
Yes, sir, getting it. If there are no questions, then we will move on. An inductor of inductance 5 Henry having a negligible resistance, its ideal inductor, is connected in series with a 100 ohm resistor and a battery of EMF 2 volt. find the potential difference across the resistor 20 milliseconds after the circuit is switched on. Switched on, it's a growth case. It's a growth case. If you look at the resistor, then potential difference across its terminals will be obtained by Ohm's law. So the current at the instant multiplied by R will be the answer. So I need to know the current at that instant, and for that I have this formula. Everything is given to you: resistance, EMF, inductor, time. It's just about putting the numbers and calculating. And once you have got the instantaneous current, the potential difference across the two terminals of the resistor would be I times R. You may need the value of e to the power minus 2 by 5, which is given to you here. If you have anything else, let me know. If you need anything else, let me know. See if you're getting this answer. 0.66 volts.
Yes, sir. Yes, sir.
If there are no questions, then we will proceed further. Think about this conceptual problem, conceptual question. You can give me your explanation, possible explanation. I can give you a clue. We say that at the center, the magnetic field is given by mu naught Ni at the center. Now mentally break this solenoid and you will get two pieces. Now can't you imagine like this, that they are similar types of pieces, so they should be contributing half of. So overall becomes mu naught Ni. And for each one of them, this point is at the end. Each point is at the end. For these two pieces, each point is at the end. See if you are able to get some clue from that. Okay, at least answer this question. If field here is mu naught Ni, and you mentally break this solenoid into two equal pieces, one starting from here, other starting from here, then field due to each should be roughly how much at this point?
So mu naught Ni
Total is mu naught
divided by
Ni divided by 2.
So it will be
Which
half.
also happens to be the end of this. Yes, and it will be for this, I mean end of this, and it will also be at the end of this. Energy density is proportional to B square. Half B square by mu naught. It's proportional to B square. So, what do you think? In which case is it going to be higher? Center or at the end?
So center.
So at the center. Sir, at the center.
It has to be higher at the center. So when you think about the result mu naught Ni, you do hear things like these, that it is same everywhere inside solenoid. But that's okay for ideal type of infinitely long solenoid. Practically, there has to be some end. So it's always safe to say that mu naught Ni is magnetic field at the center of the solenoid. Center of the long solenoid. If you attach the word long, it only makes it better. The result mu naught Ni, it makes it better. For short solenoid, even mu naught Ni is a problem at the center also. The longer the solenoid, the better will be the mu naught Ni result at the center. A coil having an inductance L and a resistance R is connected to a battery of EMF E. Find the time taken for the magnetic energy stored in the circuit to change from 1/4 of the steady state value to half of the steady state value. Steady state value will be U infinite. This is growth type of circuit. 1/4 becoming 1/2, clearly it has to be growth. Current will increase. So U1 is 1/4 of U infinite, U2 is 1/2, 1/2 of U infinite. Find the time taken. Now because the equation is for current, I equal to I infinite 1 minus e to the power minus t by tau. If we want time, we should work in current, not in energy, current. Because of that equation I equal to I infinite, and so on, which is in current, we should work in current. So that's no problem. Let's say in this case, which is at time t1, this is at time t1, current is I1 and energy is half L I1 square. So it will be this, when the current is I2, let the time be t2. So at time t2, it is this equation, this one, some cancellation, and we get the relationship between I1 and I infinity. Here also some cancellation, and we get the relationship between I2 and I infinity. I1 and I2 are related to time in this manner. I1 to T1, I2 to T2. Question is how much time has elapsed, right? It's like T2 minus T1. It's T2 minus T1, yes. T2 minus T1 is what we want. So in place of I1, putting I infinite by 2. In place of I2, putting I infinite by root 2. Well, now it should not be a problem. In fact, you can equate these two. Divide also if you want. And find out T2 minus T1. Answer is there at the bottom. See if you are getting it. And any questions, if you have, let me know.
Yes, sir.
Okay. Yes, any questions? All right. We stop at this point.